Hello and welcome to another Level 3 Technical Certificate tutorial. We're continuing our beta curve session, and in this session we're going to talk about tear. This is a typical tear curve. The tear curve is probably the most unusual of all the properties that we measure when we're doing beta curves, because it's the only one that actually rises quickly and then falls quickly. Everything else tends to go in one direction. It either increases or it decreases, unless you go to an extreme. But tear is the unusual one as far as it goes up quickly and down quickly. So in this session I want to explain why it does that. Let's go away from paper making for a minute and let's just consider a homogeneous material. Say a piece of plastic, for example. Say you've got a clear window somewhere on a piece of material or a piece of equipment that's vibrating, and say for some reason it developed a crack. If we did absolutely nothing, then the crack will spread until it gets to the other end, and then it will fall apart and you'll have two bits of plastic. So the question is, what do you do to prevent that crack propagating? Well, the answer is, let's just have a look at the end here first of all. This is what's actually going on. These lines represent the polymer chains, and this triangle is the crack. So because of the shape of that triangle, it's actually focusing all the energy. So everything's focused on that one next polymer chain, and when that one breaks, everything's focused on the next polymer chain, and when that breaks, everything's focused on the next polymer chain, and on and on and on it goes. So because we've got this focusing of the energy and concentrating on just one polymer chain at a time, it's very easy for that crack to propagate. So there's the focus. What's the solution? That's the solution. Drill a hole of sufficient diameter just ahead of the crack. Why do we do that? Well, again, let's have a look closely at what's going on. So there we have all our polymer chains again. Here we have the crack, and there we have the hole that we've drilled. Now, when the crack goes into this hole, the focus has gone. So all the energy is dissipated in all directions around the circumference of that hole, and because the energy is spread out like that, it's no longer focused on any one point, and therefore the crack does not spread. So this is what's going on. Going back to paper now, this is exactly what's going on. Here you can see one of the consequences of beating or refining. The fibres flatten because the lumen has collapsed. So you've got more fibre-fibre contact, and this is why you would expect that initial rise in strength. The other thing that's going on is the fibres are becoming more flexible. Because they're becoming more flexible, there's more area of contact, more fibre-fibre bonding, more hydrogen bonding. So again, you would expect to see an increase in strength, and that's what you get. But this is also what's going on, external fibrillation. And we're going from this situation here, where we've got all those holes that will dissipate those forces, to filling in all those holes and making a much more homogeneous sheet. And the more homogeneous it is, the more that we can focus that crack propagation, those tear forces, and therefore tear resistance will fall very rapidly. So a quick summary of what we've talked about here. Now, just 4 points to make. First of all, tear is the odd one out in all the beating curves. Tear is also known as crack propagation. The more homogeneous the sheet is, the more the tearing forces can be focused, and therefore the rapid fall in tear resistance. And finally, it's the holes in the sheet that dissipate all those tearing forces. Thank you for listening to this short video, and please feel free to follow us on any of this social media.